take a break tonight before I really get started. I have to generate some results that are absolutely essential for me tonight. So take somewhat of a break. I need some very important summation properties. So you guys, here I go. If I were to come in and sum together, how about as I range from 1 to n, some constant c? Because when you look at that sum, what does that mean to you?
You're multiplying c by n.
Why?
Because
I agree with
c
you,
is a
but
constant.
why?
And you're multiplying it n times.
But why multiply?
Because that's what you do. When you're adding the sums, you want to multiply them.
See, I agree with that. I think this is just repeated addition. I think when you look what I have on the inkboard, this is nothing more than the constant c added to itself n times. It's just that when it comes to repeated multiplication, I misspoke, sorry. When it comes to repeated addition, that's just simply multiplication by natural numbers. And so I think in the end, I simply have c times n because c is being multiplied, or excuse me, in this case, added to itself that many times, n times. And so I think quite naturally, you guys, whenever I'm adding a constant to itself n times, I should just instinctively put down c times n. You guys, I don't think this one's quite as natural. What if I were to add together the first n integers? So I think this is a bit more tricky.
N times n plus 1 over 2.
Why?
Because you're adding up all the sums and then you're working backwards and you're combining the two rows of addition. One going forward, one going backwards.
It just doesn't clearly delineate or identify where the n and n plus 1 comes
Because
from.
I'm not a math person.
Because you're
I
not
just
a math
remember
person.
things.
I think you are a math person if you say that. You know, I agree. But let me just take a break, you guys. So, give me a moment. Would you guys agree that if I take a peek at the sum of I as I range from 1 to n, you guys, isn't this short notation, concise notation for saying this? 1 plus 2 plus 3 all the way down to
n.
I agree. The very last term is an n. Actually, you guys give me a second. Let me backtrack a few steps. I think this term's predecessor is just n minus 1. I think this term's predecessor is n minus 2. If I can write it. Oh, you guys, that was so much fun. Let me say it again. The sum of I is I range from 1 to n, and I am going to say it again. I'm just going to write things backwards. Isn't this n plus n minus 1 plus n minus 2 all the way down to a 3 plus 2 plus 1? It's just that column by column on the right-hand side of the equal sign. You guys check out what the heck really happens in the very first column. What's the sum of these two beasts? It's just 1 plus n. What's the sum of these two beasts?
1
Which
plus n,
implies to
or 2n minus 1. Or 2n minus 2. 2n minus 2.
N
Is
plus
my
1.
arithmetic okay? And the sum here is
N plus 1.
same thing.
Yeah.
Sum here is
N plus 1.
and another n plus 1, another n plus 1. I think column by column, you guys. Every time I add, I'm just going to get an n plus 1. Oh shoot! How many times did I do that? I did it n times. So if I'm going to add n plus 1 to itself n times, isn't that the same as n times n plus 1? It's just that on the left-hand side of the darn equal sign, if I'm adding the sum to itself twice, don't I get, well, just twice that sum? And now in isolating the sum of i's, I range from 1 to n, I'll divide both sides by 2, and you guys, here's a nifty little formula for my back pocket, namely the sum of the first n integers can be interpreted as a ratio of this product to 2.
Why is it over 2?
Because in this equation right here, I divide both sides by 2 to isolate the sum. So if you can't read it, let me write this up here. That gives me 2 times this particular sum.
Why is there 2
Yeah.
of the sums?
Well, the reason why I have a 2 out there is because below this horizontal line, I simply added what was above. Adding this to this is gonna give me two of those things. I was just combining those equations using the addition technique from MAPD. And everybody, dividing both sides by 2, I think that merely leaves me with the sum of this particular beast to be n times n plus 1 over 2. Well, I'm afraid I need another nifty little identity. Namely, how the heck I can take the sum as I range from 1 to n of I squared. You guys, this time around, instead of deriving out of theta, can I just give it to you? It's n times n plus 1 times 2n plus 1, all divided by 6. It's just that you guys, with this particular identity, this relationship, is a statement based on n, where n is ranging over the positive integers. And a lot of times when I want to prove a mathematical statement relying on the set of positive integers, a typical technique of mathematical proof is called mathematical induction. No response. Mathematical induction?
Mathematical induction works for series.
It truly does. But you guys, give me a show of hands. How many of you are familiar with mathematical induction? Remember the name. So typical discussion of topic in a standard Math 12 course, or pre-calculus course, or maybe college algebra course. Here, college algebra Math 12, pre-calculus Math 29.
My college algebra course let me down.
Another reason why 12 is not a good substitute for.
You know, I have to confess, I really don't teach Math 12 that often. I didn't know that. I typically discuss the topic anyways.
No one else does.
Do you understand what inductive reasoning is? Wait. How about this? It is true that every day in my life, when I'm risen from bed, the sun has risen. That being the case, is that good enough reason for me to say the sun's going to rise tomorrow?
No, you might not.
Yeah, well, I might not. True. And the sun might not rise tomorrow either, right? And the point is, I can't just rely on particular instances of my past and conclude some general statement about what's going to happen next. Inductive reasoning is a type of reasoning that most mathematicians and scientists do not abide by. Inductive reasoning basically, for the most part, takes particular occurrences in the past and produces some general statement for the future. Something else negative about inductive reasoning is it typically relies on perception, human perception. I had to rely on what I saw, what I experienced every day when I woke up. Typically, scientists and mathematicians will abide by deductive reasoning, which works in a completely opposite direction. We make some statements or have some premises about something very general and conclude something very specific, and it doesn't rely on my perception. For example, what if I told you guys every single car ever produced is painted red? And you did not see me come to campus, and I told you I own a car. Now, without going out to the parking lot, couldn't you conclude sitting in your chair in this room that my car is painted red? That's an example of deductive reasoning, where I've got some general statements up here, and I conclude something very specific, and it does not rely on perception. Now, I have to confess, most mathematicians abide by a certain type of inductive reasoning. It's called mathematical induction. Personally, I believe in this. I think it's solid. And here's how the reasoning goes. If I've got a mathematical statement, P, that's true for all natural numbers n, all I have to do to prove that statement is true is show it's true for the smallest such value of n, typically 1, but it could be something else. And then if I can show you, the reader, that assuming this statement is true for an arbitrary value of n, call it k, if I can show you it's true for the next integer k plus 1, then I believe I've proven that statement is true for all natural numbers n. Because it's sort of like a domino effect. I proved to you that it's true for the very first domino that falls. And I've proven to you, no matter what domino out here falls, the next one's going to fall as well. Now, there are some mathematicians out there who do not abide by mathematical reasoning. There are some mathematicians who do not believe in mathematical induction. Yes, sir.
Are there any cases for which that's not true? That it doesn't work?
See, I think if I can go through that process, for any mathematical statement, evaluate n, where n is a natural number, if I can go through that process and come to those conclusions, then I believe the statement is true. There are some mathematicians who don't believe in it. You guys, not too much of a tangent. There are a couple of gentlemen out of UC Berkeley in the 60s. They've proven that no matter how advanced we become in our society, with the foundations we have for our computers, even if we really develop well parallel processing, artificial intelligence, a computer would never be able to understand that process. And those mathematicians are called constructivists. And constructivists do not abide by mathematical induction. They created a weaker version of it so that someday in the future, if we can develop artificial intelligence, a computer will be able to understand that weaker process of mathematical induction. But I'm not of that camp. I believe in it. So everybody, I'm in trouble.
So in the mathematical world, that's not real math?
I think for those mathematicians in the constructive world, that's not real math. All right, we'll get rid of it. So you guys, I'm in a bit of trouble. I do need to take a short break. I want to prove to you the statement's true using mathematical induction. I have the right to come into class tonight and do this. It's pretty bad. I need this so the rest of the night tonight I can talk about evaluating integrals, discussing properties of integrals. So, give me a moment. To prove that this statement is true for all natural numbers n, I will first show that this is true. For the very smallest possible value for n over here, which by the way is n equals 1. So you guys humor me. If I take a peek at the left-hand side of the equal sign, wouldn't that just give me the sum of I squared as I ranges from 1 to, I'm losing it,
N.
what was that?
N.
I think just 1. Which, by the way, means when I plug 1 in for I get this. Plus, when I plug 2 in for I get...
You don't plug in nothing.
Yeah, nothing. Actually, the last value for I have is just positive 1. I'm done. I'll evaluate. By the way, if I take a peek at the right-hand side of the equation over there, replacing n with positive 1, wouldn't that give me this? But isn't that just simply this? Oh, shoot. That's just a 1. So haven't I very quickly shown you that this trivially is true? The statement is true for the smallest such value of n, which is positive n. Well, you guys, that's always the easy part of this particular theorem. Or, excuse me, that's always the easiest part of this type of proof. I think where the work is when I assume that that statement over there is true for an arbitrary value of n. I'll call it, I'm just making this up out of thin air. How about k? So let's assume the sum as I range from 1 to k of my I squared is equal to my k times k plus 1 times my 2k plus 1 all over 6. You guys watch my parentheses. I'm going to show you that this particular statement over there in terms of n is true for the next integer, which is k plus 1. We will show that the sum as I range from 1 to the next integer, which is k plus 1 of my I squareds, is equal to my k plus 1 times my k plus 1 plus 1 times my 2 times k plus 1 plus 1 over 6. You guys, I'm putting this in parentheses because that's what I'm going to show. Now to show that, I think I need to start with what the heck is on the left-hand side of the equal sign circled in red and mathematically deduce that is equal to what you see inside that blue circle. So let me do just that. Let me start off with what's on the left-hand side of the equal sign. That is to say, the sum is I range from 1 on to k plus 1 of my I squared. Do you guys agree that an expanded form, that's nothing more than this? All the way down to the very last term, which is a k plus 1 squared. You guys, just for clarity, can you guys give me just this predecessor? What's the previous term? Yeah, I agree. And I think this is equal to, actually, do you guys see where I'm going with all this? I'm going to show this is equal to my destination expression, which is right here in that blue circle. Now to do that with this mathematical induction process, somewhere along the way I'm going to use my assumption. In fact, this assumption is so important, can I give it a name? I call this my Math
Geometric,
29 graduates, my
geometric sequence?
inductive
Um,
hypothesis. Somewhere along the way, I'm going to use that inductive hypothesis. Oh, shoot. I can. Actually, you guys take a peek at these. Isn't that nothing more than the sum of I squared as I raised from 1 to k? So using my inductive hypothesis, I think what's sitting above the brace is nothing more than my k times my k plus 1 times my 2k plus 1 all over 6. Oh shoot, I forgot my last term, I'll put it in. Plus my k plus 1 squared. And you take a peek at my destination expression, which is nothing more than k plus 1 times my k plus 1 increased by 1 times my 2 times k plus 1 all over 6. You guys humor me with this. How many fractions do I have? One. Well, actually, I misspoke, didn't I? In my destination expression, I've only got 1 fraction. Shoot, how many do I have up here?
2
So how am I going to bridge the gap?
combined fractions.
Combined fractions. Piece of cake. This is just itself over 1. But multiplying top and bottom by 6, doesn't that give me common denominator? I think in the end, all I really have sitting in front of me is my k times k plus 1 times my 2k plus 1 plus my k plus 1 squared. Oh, actually, I forgot a lingering factor of 6. All over 6? Because I'm tired. I need to beat that clock. Because I'm tired. What's easier, to FOIL out or distribute the k in first?
Factor out the k plus 1.
Yeah, I would. I'd do neither. I think I got 2 terms upstairs. I'm going to be lazy, you guys. I got a red binomial factor in common. I'll pull it out. And here it is. Now, what the heck remains standing on either side of the addition operation of black as remaining factors? Ah, piece of cake. Just this. And this. Sorry if you guys, I'm clumsy and not using my board space properly or efficiently. If I were to continue to clean up, wouldn't that give me the product of this binomial? Times my 2k squared plus k plus 6k plus 6. Or shall I say, my k plus 1 times my 2k squared plus, I don't know, I can't read my own writing. Is that 7k? And I think in addition to that, oh, you guys don't know where to go next with this. Does that trinomial factor nicely? I asked. Does that trinomial factor nicely? I can ask a third one. Yeah, it factors nicely into k plus. Really? I always come with a 2. Tell me if I'm wrong. Yes? No? Is that okay? Oh, by the way, isn't that the same thing as this? Is that a k plus 1 times how about a k plus 1 increased by 1? Times 2k plus 2 plus 1. It's just with 2k plus 2, isn't that the same as this? Which is exactly what I want to. So I think via mathematical deduction, I can therefore conclude that it is indeed the case that the sum of I squared as I arranged from 1 to n is indeed n times n plus 1 times my 2n plus 1 all over 6. And this is true for all natural numbers n. Are you happy?
I don't know, I'm a constructive mathematician.
You want to be a constructive mathematician? You don't believe in any of this?
No.
Actually, those constructivists, they weren't unique. There is a movement by a name of mathematician by the name of Brouwer at the beginning of the turn of the century. And he constructed a movement called the Intuitionists. It's just, it didn't last for, I don't remember, something like 10 years, seriously. It just kind of died out. And so these 2 gentlemen at the UC Berkeley actually regenerated that Intuitionist movement. So they call themselves constructivists.
So if you don't like something in math, you just name yourself something and just disregard that.
Well,
idea.
you know what, maybe it's what Broward did, but these gentlemen at UC Berkeley didn't. I mean, they were really after one particular item, which is setting ourselves up for the future to be able to have computers understand these proofs.
So,
You guys attack me, come on, you're the one paying money to be here. Anything that's unclear on the board? Because
you-
I'm getting nervous. You guys are telling me, most of you are telling me that you can remember discussing mathematical induction as a proof technique.
can you just explain to me really quickly, the actual equation there, when we have the 2n plus 1, where did the 2 come from there? Or why don't
You
we
know
have
what,
n
that's
plus
a good
2?
question. Yeah, I don't know if you guys noticed this, but up here, I proved this out of thin air.
Yeah.
You know, when I wrote this on the board the first time, I left the right-hand side blank and I derived it out of thin air for you. But with this particular statement down here, I did something very different. I pulled a fast one on you. I actually gave her the result and proved it was true. And so I did something completely different. And so I didn't tell you where the 2 really came from if I had to generate this thing out of thin air. I'm just saying, I recognize the pattern. Let's test to see if the pattern works by using mathematical induction.
Can you tell us where the 2 came from?
You know, technically speaking, it really comes from the fact that I'm just adding fractions, to be honest with you. And the way things factor nicely, that's why I've got that
Okay.
factor 2k plus 1 in there. As well as the previous one, which is k plus 1.
Okay.
This is the notation.
Which one?
The last character.
Oh, sorry, you guys, tell me if I'm using something new. When I use I use a symbol, haven't I?
Well, yeah.
That means-
We've seen that over and over.
So for all n as elements of the natural numbers.
It was the natural numbers. And then
Yeah, I tend to use an uppercase n. And I like the bold faces so you understand it's not a variable, it's a set of natural numbers. That's just that I'm writing on the ink board, I can't boldface. So I typically put a vertical slash to its left-hand side. Oh, you guys, there's one left. I'm not going to prove this. I prove the same way. That if you want to sum together I cubed as I arranged from 1 to n, you simply get n times n plus 1 over 2.
It's just repeating.
So it's just the same as I?
Oh shoot, it can't be. I guess it's got to be wrong.
That's wrong.
So,
Oh.
I'll modify it. It's the same thing. Raise the second power. My point is easy to remember.
Okay.
But we don't have to memorize anything.
So if it were I to the 5,
I'm sorry, Brad, I didn't catch that.
so if it were I to the 5 there instead of I to the 3?
You know what? You and I aren't going to need to go that far.
Okay.
You guys, I know it sounds like I'm switching gears again. I need to discuss something different. So, do you think I can get rid of this?
Do it.
Go ahead.
No other questions? All right.
Actually,
Well, yes.
just kidding.
You know, I think what I want to discuss next is one of the funnest things we're discussing this entire semester. No, not tonight. Not tonight. Maybe Wednesday night. I shouldn't say maybe. Definitely Wednesday night. Come on, you guys, fast. What's the area of the rectangle? It's 6. What's the area of the circle? Pi r squared. I mean, easy stuff, right? You know that I don't think it's not easy? What if I had x-axis, y-axis? I had the graph of some function y equals f of x, or excuse me, the graph of equation y equals f of x. What if I asked you over the interval from, I'm making these letters up again out of thin air, you guys, how about a to b? If I asked you for the area underneath the curve from a to b, do you think you could pull out of your back pocket a nifty little formula from high school geometry to generate that area value?
No.
Yeah, I don't think so. I mean, the area of what? I mean, I don't know what the function is in this particular case. It's being abstract. So tonight, I want to develop techniques for coming up, at minimum, with an approximation technique. But before we're done tonight, a way of coming up with the exact area underneath the curve, at least in some special case scenarios. So everybody, here's my job. I'm going to take the interval from A to B, and I'm going to subdivide it into n smaller intervals. For example, if I take that value of A, I'll rename it. I'll call it, how about x of naught? And here's an x of 1, and here's an x of 2, and here's an x of 3, all the way down to the very last value of B, which I'm going to sometimes refer to as x of n. I even have its predecessor, x of n minus 1. Actually, you guys, to make this a smooth flowing argument, do you think I could just come in and talk about the arbitrary I subinterval from x of I minus 1 to x of I? Next, with my red pen, I'm going to choose a value of x in each and every one of those n subintervals. I will choose x of 1 bar as a particular item in the very first subinterval. And I don't care where it is. In the second subinterval, how about this tick right here? I'll think of that as x of 2 bar. And here is an x of 3 bar. And here is an x of I bar. And down here, that's going to be my x of n bar. And so I think when I use these x of I with a bar over it, it's just a particular choice of value for x within each of those subintervals.
Wait, to any point within the interval? As long
Yes.
as it's the same type, or the same,
what?
the same, like, not like point, but the same position within the interval and each.
See, I disagree. That's why I was trying to be goofy on the board. Notice how my x of 2 is really, x 2 bar is really close to x of 2.
Oh, I see.
But notice how my x of 1 bar is closer to my x of naught.
Okay.
And so I really intended for all these red x values with the bars over to be arbitrarily chosen with each of those subintervals. Now what I'm going to do with those x values? With my blue pen, I'm going to go straight up the curve with that x value, for example, x of 1 bar, and use that as the vertical height of my first approximating rectangle. You guys, I just want you to be honest. Is it easy? Just a yes or no answer. Just yes or no. Is it easy to compute the area of the rectangle?
Yes.
Yeah,
Yes.
I think it is. I think the area of the very first rectangle is nothing more than its height times its width. Oh, shoot, you guys, I'm running out of letters. When I run out of letters, where do I typically go?
Delta.
The Greek alphabet. And I'll choose the uppercase Greek letter delta and talk about the change in the first subinterval, or how about just saying the first subinterval's length. I call it delta x of I. I meant delta x of 1. Now, using my red tick in the next subinterval, if I use x of 2 bar to go straight up to the curve, use that as the height of my second approximating rectangle, then I think right here, solid blue, is nothing more than the area of the second rectangle. And say, well, I will add to that my a sub 2, which is nothing more than f evaluated x sub 2 bar times my delta x sub 2. Oh, you guys, I'm running out of room. Do you think I can just cut to the chase? Can I just talk about, not A1, not A2, but can I talk about the area of the arbitrary ith subinterval, which here too is going to be computed by looking at the height of that ith approximating rectangle and multiplying by its width? I think I'll even go down to the last one. Use x of n bar to go straight up the curve. Use it as a height of my nth approximating rectangle. And how about saying this? If I take a peek at the sum of the area of the I rectangles, as I range from 1 to n, I think that'll give me an approximation for the area of my curve. Right?
No.
Well, I mean, maybe this is why it's an approximation, but what about all the extra space that's above the function?
It's lousy, isn't it?
Yeah.
I think
it
with
just-
that first approximating rectangle, I'm probably over-approximating the area of the curve.
for quite a bit.
I think with the second one, I don't know, kind of even. I think with the ith one of my picture is pretty much underestimating the area of the curve. So I think what I'm doing on the board is rather crude. However, if you allow me to have more and more subdivisions, you have to confess this might be pretty significant. I mean, what if it's, if A is equal to 1, B is equal to 3, and I choose n to be 7,000? With 7,000 subintervals, as long as their widths are going to be pretty small number as a size, I think this might be a decent approximation technique. And you know what, tonight, you guys, I promise you, I'm not staying here. Tonight, I'm going to take this, no pun intended, to the limit. We'll be taking a limit of these sums, and we'll be able to come to the exact area. Maybe not
Okay.
every case scenario tonight. So, David, you didn't like what I wrote in the board, you're shaking your head.
Well, I think I figured out. I thought, for some reason, I thought you took the f of x, which is just the height. But
Is that-
you put area there, so you took the whole area.
You know, I see your point, I'm gonna write your.
Is that an AI or a delta I?
It's the same question.
Oh, wow.
Ah, see, I was thinking it was a delta.
You guys are so happy I typed this in,
Yeah.
I know. And by the way, this is the same as the sum as I plays this game of, okay, David, I'm gonna go your direction. I think the area of the ith rectangle could be interpreted as f evaluated at the, I don't know, an arbitrarily chosen value of x in the ith subinterval. Times is horizontal width. Actually, what do you guys think I can do to come up with the exact area?
Take the limit of that.
Take the limit as what does what? I can never take a limit without having something to something.
To infinity.
You know what, you guys, in a few minutes, I like what you're saying. In a few minutes, I'm going to talk about n going to infinity as well. Right now, I can't, because when you come to see each of these subdivisions, they're not of the same length. This length is different, that one is different, that one. You know, a typical thing I find in a lot of calculus texts at this level is that the author doesn't allow that kind of freedom. In the author text, I have to commend for that reason. He really does like to say, let's consider an arbitrary subdivision interval from A to B into n subintervals. As a mathematician, that's what that's how I think. As a mathematician, I hate to use a definition that doesn't have that kind of freedom. Now, because of each of these horizontal widths being of different length, what I'm going to do is I'm going to take the limit of this sum as I play this game of these beasts. And I'm going to take the limit as the largest subinterval, I'll just call it delta, goes to 0. I have some words for this in English. In English, I sometimes refer to this as the norm of my partition. It's really the largest sublength in a subinterval from A to B. And I think if the largest one goes to 0, all the others are going to go to 0 as well. Now, you guys, I have to confess, I don't have to play this game. You know, technically speaking, what I could do is this. Here's my x-axis, here's my y-axis, here's my function. Here's my A, here's my B. I can subdivide the interval from A to B into n subintervals, just like I did before. What if I came in and did this in such a way that each of those subintervals over there in the middle inkboard have the same length? If they have the same length, it's sort of like in high school geometry talking about a pentagon in which each of the interior angles and each of the sides has the same measure. If you had a pentagon where each of the interior angles and each of the sides had the same measure, what would you subclassify that as? High school geometry.
Wouldn't all the triangles in the pentagon be the same size then? Like if you divided the 5 triangles,
What do you mean same size? I'm nervous about
they
that.
have the same area. So if it went to the center of the,
Oh, I'm sorry. You're saying emanating from the center of the pentagon, like that.
yeah.
You know, I have to confess, those triangles will not have the same area unless that pentagon had that very special quality I just mentioned.
That's what I'm saying.
That all these interior angles and sides are going to be the same, have the same measure. That's true. That's true. I'm not even going there. I want you to be lazy. We're lazy than that. How would you subclassify such a pentagon? Oh, you guys really? A regular pentagon? For that reason, okay, never mind. That didn't work. For that reason, do you guys mind if I talk about this kind of a subdivision from A to B as a regular subdivision? Or can I be more mathy than that? Sometimes when I subdivide something, I refer to it as a partition. So maybe in English, I'll refer to this as a regular partition interval from A to B, which means I'm subdividing A to B into n subintervals, each of which has the same length. Matter of fact, I'll refer to the length of each one of these as delta x of I. Oh shoot, you know what? I take that back, I don't have to. Since each of them have the same length, forget about this I garbage. I think I'll just call it delta x. And I think if you take a peek at my picture, life is a 100% piece of cake. Because I think the length of each of those subintervals, quite naturally, is going to be nothing more than the length of the whole interval from A to B. Divided by how many I'm creating. So I think my b minus a over n is going to be my delta x. That will be the horizontal length of each of those subintervals. But again, unlike this picture over here, that is to say if I create a regular partition for the interval.
So what's the x sub I minus 1?
You know, all I really meant is that when it comes to this ith subinterval, I will think of the right endpoint as x sub I. It's just that the left endpoint of the interval is going to be one less.
Yeah, okay.
That's all. Nothing.
The x sub minus 1. Oh, okay, because it's the same thing. All right.
It is really the same thing. It's just for the nth subinterval, the right endpoint will be x sub a. Well, the left one will be one less than that. Nothing more. So everybody, next, I know we need to take a break. But before we walk out for 10 minutes, I still think to do what I did over here in the picture in the middle board, I've got choices. I can choose my x sub 1 bar anywhere in this first subinterval. But what if I made a rule? Every time you choose your x sub I bar, you do it the same way. And if I choose it as the left endpoint of each of these subintervals, I might refer to it as my left endpoint rule. If I choose the x sub I bar as a right endpoint of each of the subintervals, I might think of this process of approximating the unit curve as using some kind of right endpoint rule. Maybe I can consistently choose the midpoint of each of these subintervals. I can do that just as well. Also, before we take a break, I'm getting nervous with my choice of words. You know, I don't have very good words, so can I just create some more vocabulary? When it comes to a big sum like that, it's so important I give it a name. I refer to it as you guys reading ahead of me and going online. Yeah, I read on.
Is that how it's pronounced?
So, it's pronounced read on.
It's not run.
R-I-E, that's sound.
It's German.
I mean, it's German, isn't it, you guys?
Yeah.
I only speak French and maybe a little Russian. I don't speak any German. Am I pronouncing it correctly?
I-E is on E in German, while E-I is pronounced as I, so.
Gotcha, so I am correct.
It's a Riemann.
It's a Riemann sum. It's settled. That's always how I heard it. I'm a mathematical word. So you guys, we need to get more serious after the break. Like I said, by the end of tonight, we're going to be able to compute some areas we've never been able to compute before. But unfortunately, I need a combination of what I'm discussing now with Riemann sums, as well as those formulas over there on the left-hand board. So let's not forget them.
What happens with the functions that meet the x-axis?
Ooh, what a good point. I'll discuss that after the break. Since it's below the x-axis, I think f evad at x sub I bar is going to be a negative number. I will get negative area.
Okay.
I sometimes say these sums give me